chap, and then I saw her in the crowd, and I looked her in the eyes.
Welcome to Wake Up in Astronomy. My name is Professor Scott Croom. I will try to answer your questions today. I work at University of Sydney, and what I do most of my time is I'm researching how galaxies form and evolve. Galaxies are big groups of stars spinning around our universe. I'm trying to understand how they work and also how the massive black holes in the centers of them are impacting galaxies. So I'm going to answer some of your questions today. And we're going to start off with a question from Saskia. That question is, what is the coldest temperature in space and where is it found? That's a great question. Through most of space, the temperature is very, very cold. Typically, the coldest temperature is about minus 270 degrees. And that's because that's the temperature of light radiation that was left over from early in the Big Bang. But every now and again, in small pockets around stars and that have dense gas, the temperature can be even colder than that. Maybe minus 272 degrees. That's about the coldest you can get. Second question is from Cormac. His question is, how are black holes formed? So black holes is a subject close to my heart. I spend a lot of my time working on black holes. Whenever you have something like a star, it's a battle. It's a battle between the gravity trying to suck more matter in, but then the star producing energy and heating the gas in the star pushing out. So you have the pressure pushing out, you have gravity pulling in. Eventually, what will happen when the energy from the nuclear fusion in the star stops is you will have no more energy to produce the pressure to stop the collapse. At that point, gravity takes over and comes all the way, and if the star is big enough, it will collapse all the way down to a black hole. So it's really that battle between gravity and gas pressure. Our next question comes a little bit closer to home. This is from Zachary. How does Mars have rust if there's no water and no oxygen? That's a really good question. Mars is known as the red planet. The reason it's red is because the surface has a very high levels of iron oxide, and iron oxide is rust. That's a combination of iron and oxygen. Now, we know at the moment that Mars doesn't have any oxygen in its atmosphere, or very little, and it has no water, liquid water, but it does have water under its surface. There's also good evidence now that Mars has had in the past water on its surface. And so our best guess is that the oxidization of the iron, the combination of the iron and the oxygen, happened when there was, in the past, liquid water on Mars. Our next question is from Sebastian. Sebastian asks, we cannot be the only evolved species in the universe. Is there anyone else out there? Well, that's a great question, and I wish I knew the answer. What we do know is that when we look at other stars in our galaxy, many of them have planets around them. We've now discovered about 3,500 planets around other stars in our galaxy, and that number is really only limited by the number of stars that are close enough for us to be able to look effectively. So we know there are lots and lots of planets out there. We even know that some of them are good for hosting life, and in that case, what we think the best conditions for hosting life, at least similar to that on Earth, is that a planet is close enough to a star that it is hot enough that liquid water can exist on the surface. So you don't want it too close, the water would boil. You don't want it too far away, the water would freeze. And we do find some planets that are that distance, that Goldilocks distance, away from a star, and they potentially host life. But of course, the question is, do they host life? And that we really don't know yet, and we won't probably know for some time. The real trick there is, even though the conditions might be reasonable, we have really very little idea about whether the special chemistry that happens to make life occur can happen on all those other planets. We know it happened on Earth, but that's the only place we know that it actually happened. Okay, so our next question goes to the other extreme of size, to the universe as a whole. This is from Amelia, who says, I know that astronomers say that the universe is infinite, but there has to be an end at some point, right? Well, there's two different answers to that question. What we do know in time is the universe has a fixed age. The universe is about 13.8 billion years old. So the universe hasn't existed forever, but it started at a fixed point in time about 13.8 billion years ago. And that means that when we're looking back in the universe, we can't see forever. And the reason for that is that it takes light, the light coming from distant stars and galaxies, time to travel from them to us. And so there is a limit to how far we can see in the universe because of the time it takes light to travel. However, that doesn't mean to say the universe is finite in size. As far as we can tell, all our measurements suggest that the type of universe we live in is one that does go on forever. And we can measure that by measuring the shape of the space in our universe, by looking at distant galaxies, the distribution of them in space, and by looking at the leftover radiation from the Big Bang, we can see that the universe looks like it goes on forever, even though we can't see that far. Okay, the next question is from room 9. They ask, is the universe growing bigger or staying the same? Well, the universe is expanding. But we have to be really careful that we understand what that means. Because I'm not expanding, you're not expanding, your classrooms aren't expanding, and that's because the atoms in your body are holding you together. But as you go to larger and larger scales, on the scales that are bigger than galaxies, millions and millions of light years, those aren't held together by strong forces. They're separated by very large distances, and so they can fly apart. And in fact, what we see in our universe is that the galaxies on the larger scales are all moving apart from one another. And in fact, even more surprisingly, what we find is that the speed that they're moving apart from one another is actually increasing. So they're getting faster, not slower. Our next question is from Abram. And that question is, what makes the Earth rotate? This is a really interesting question. And it really comes down to how the solar system formed. The solar system and stars in general formed from a large cloud of gas. And that cloud of gas wouldn't have been completely uniform and smooth. It might have had a little bit of rotation. It would have been maybe a little bit of gravity stronger on one side than the other. And that would have had a little bit of rotation in that large cloud of gas. But what happens as that cloud of gas starts from a large scale and collapses down to form a star is that it spins up, it speeds up. Exactly like if you're sitting on a chair and spinning round and you put your legs out, you go slow, you bring your legs and arms in and you speed up. That's called conservation of angular momentum. That's speeding up as you get closer in. And that's exactly what happens when stars form. And so when stars form, they spin up, and in fact the sun is spinning, and all the material around the sun that formed the planets was also rotating around the sun. And so the Earth spins because all the material that it formed from was also spinning. All the planets also spin in the same direction around the sun. Great question. So next question is from Michael, and Michael's asking, what keeps the sun in its place? Well, that's a really good question, because actually the sun doesn't stay fixed. The sun is a star, one of billions in the Milky Way galaxy. The Milky Way galaxy we see across in the night sky, a big band across the sky of stars, and that's because we're sitting in a disk. We're sitting in a flat distribution of stars, what we're looking at edge on. And when you look to see how that sun is moving, the sun's actually rotating around that disk. So actually the sun isn't in place, it doesn't stay still, it actually is moving. But it doesn't move in any random direction, it doesn't move in a straight line, it rotates around the galaxy because of gravity. Just like the planets rotate around the sun because the sun's gravity keeps them in place, so the sun rotates around the center of the galaxy because the total mass of the galaxy causes gravity to keep the sun rotating. Okay, so I've got a question from the chat, which is, what happens when things go into a black hole? That's a great question. A black hole really is just a point in space where everything collapses down to essentially to a point. Things are pretty ugly when you fall into a black hole, and that's because the gravity is so strong. So if you fell feet first into a black hole, what would happen is the gravity at your feet would be stronger than the gravity at your head, and you'll be stretched out like spaghetti, which is pretty nasty. I'm afraid that sort of the sci-fi movies that talk about space travel going through black holes are science fiction, not science fact. But great question. Okay, so our next question is from Abraham. How come the sun has not run out of gas? Well, the simple answer to that is that the sun hasn't run out of gas yet because it is huge. The sun has been burning its nuclear reaction in the middle of the sun for about 5 billion years. And what it's doing all the time is it's taking hydrogen gas, it's colliding those hydrogen atoms together at very high temperature, and it's converting that hydrogen to helium, which is actually, helium is the gas that you put in party balloons that makes your voice squeak. But eventually, in about another 5 billion years' time, the center of the sun will actually be mostly helium, and there won't be enough hydrogen there to burn. And so at that point, the sun will actually run out of gas. What will happen then is that the center of the sun will collapse, and it will start burning the helium into other elements. The extra temperature from that will puff up the outside of the sun and turn it into a red giant. So our next question comes down to practicalities of space travel, and PJ asks, how do you produce power in space? Well, the simple answer is just the way you do on Earth. However, the important thing about producing power in space is that you want it to be easily renewable, you want it to be lightweight. So, for example, you wouldn't want to be sending a rocket up into space with a large amount of coal that you wanted to burn. Coal's heavy, and once you've used it, it's gone. The most effective way of getting power in space is using solar panels, and so many satellites, for example, the International Space Station, have solar panels on them, and that is the most effective way of getting power from in space. In other cases, you might have even nuclear power on a satellite, especially if you're going to travel a long way away from the sun, where solar power is not so strong. Okay, and so our last question of today, and our question of the day, is from Arjuna. And their question is, how do scientists weigh the universe and calculate there was such a thing as dark matter? Well, that's a really great question. One astronomers still spend a lot of time trying to grapple with. The reason we think there's this thing called dark matter in the universe is because we can see the effect of things in space, effect of gravity on things in space. So we can look at galaxies and we can see how fast the stars are rotating and how much gravitational force is required to hold them together. When we count up the stars and we compare that to how much mass we need from gravity, the two don't add up. And so that's when we first suggested that dark matter, something other than our normal matter we see in planets and stars, must be there. And that's all the questions I think we have time for today. Thank you very much for being part of this. I hope you enjoyed it and I hope you learned lots.
You